you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, this is Mr. T, and today we have another math tutorial. And today we're going to be examining lists of numbers. So our lists are in sets, so sets are bounded by these curly braces. And in an example here, we've got a finite number of items in the list. So in this case, this list has 5 items. And over here, we have a list that has 5 numbers explicitly listed, but then we have this ... meaning that that list continues to infinity following whatever pattern we have. So these lists of numbers are referred to as sequences. So today's topic is all about sequences, and there are finite sequences and infinite sequences. Most of what we'll be working on will be these infinite sequences. When we talk about sequences, we identify each number in the list by its position or its term number or element number. So when we are counting the terms, and we're going to frequently be using the letter N to represent which term number we have, we start counting by 1. So term 1, term 2, term 3, term 4, term 5. Here we've got term 1, 2, 3, 4, and 5. Now, most of the sequences that we're interested in mathematically will have some sort of pattern that we can identify, and if we can identify a pattern, we can also write a formula for those. Because what we have here is a mapping between a term number and its element. So term 1 maps to 2, n equals 2 maps to 5, 3 equals to 8. So these sequences are also another representation in mathematics of things called functions. Remember, functions take a input, which in this case would be the term number, and produce a unique output. So let's look at our first example here and see if we can find the pattern. And maybe you could see that in going here on from here to here, we added 3. And going from here to here, we added 3. And again, plus 3. And again, plus 3. So every term we are adding 3. So let's write a rule for that. So now we're going to write two kind of rules. We're going to write something called a recursive rule. These are the easiest type of rules to write. And the recursive rule for this, now normally we use the letter A to represent a sequence. And these individual items in the list are subscripts on that. So this would be A sub 1, A sub 2, A sub 3. So if we write a recursive rule for this sequence, we've got to start the process. So A sub 1 is equal to 2. And then to get the next item in the list, or a item in the list, we are taking the previous item plus what we're adding here is 3. So in this case, this would be, since this is a finite list, would be for values of n going from integers, going from 1 to 5. Again, A sub n represents the nth item in this list. If we do n minus 1, that's going to be the previous term. So if n was 3, the previous term would be A sub 2. Now, the recursive rule, as you can see, was easy to write other than getting used to this subscript notation. But it's not all that useful, because if we wanted to find, say, especially in an infinite list, if we wanted to find, say, the 50th item in the list, we would have to recursively or one by one start at the beginning of the list and work through. So frequently what we're interested in is trying to write an explicit rule, which is essentially a function definition for our sequence. So if we look up here, when we get to rule 2, so this number we've added, how many times have we added 3? And this one we've added, so let me write under here, this number that I'm going to put in here will be the number of times we added 3. So here we haven't added any 3s. On this number we've added 1 3. Here we added a 3 and a 3, so we've added 2 3s, 3 3s, 4 3s. So we can see the number of 3s that we added is 1 less than the n value. Because remember, these numbers are the n. So we could write our rule here. If we're looking for the nth item, it's going to be the first item and then how many 3s that we've added. So, and what we said was that we've added 1 less than n. So if I want to represent adding 5 3s, that's multiplying 3 by 5. So here we want to multiply 3 by n minus 1. Now this is a explicit formula, and we could easily find, say, the 100, well, this is not an infinite list, so it wouldn't make sense. So here we should be saying that the n values go from 1 to 5. It's not defined after that with this sequence. This rule does not apply beyond those terms. So we'll talk later about, say, finding the 100th item, but you could see if this was a infinite series here, we could plug in 100 for n, so over here we would be multiplying by 99 3s and then adding that to 2. So let's look at this over here, and let's also make both a recursive rule and a explicit rule. So here we're starting with 18, and here, going from here, we are subtracting 4, and then I'm subtracting 4, I'm subtracting 4, subtracting 4. So to get our next item, we take the previous item, remember that's a to the sub n minus 1, and then we are going to subtract 4. And this is for n equals to 1 to infinity, where n are positive, so essentially n are the positive integers. Again, this was the recursive rule. Let's look at the explicit rule. Like we had here, we are here I've subtracted 1 4, 2 4s, 3 4s, 4 4s. So the number of subtractions or adding of negative numbers I've done is 1 less than n. So here our explicit rule would be our first number, and then here minus 4, and we are doing n minus 1 4s. So if we wanted to find, say, for this, the 100th term, so that would be a sub 100, we've got 18 minus 4 times 99. So that's going to be 18 minus 396, which would give us negative 378. Now this type of sequence is one of the common types that we have, where we are having a repetitive addition or subtraction, and this is referred to as an arithmetic sequence. One of the main types that we're going to have are arithmetic sequences, and they're noted by having a common difference, or between adjacent numbers. So the difference here is 3, 3, 3. Here the difference is the negative 4, or it's also representing repeated addition. So let's look at some other sequences. Okay, so if we look at these, now here if we tried the same thing before, I would be adding 1 adding 2, adding 4. So there's not a common addition here. But if we look at this, we may notice that each time we're doubling. So this was times 2, and then times 2, times 2, times 2, etc. So our recursive formula here, so let's do both. We'll do both recursive rules and we'll do an explicit rule. And the recursive rule here, again, when we write recursive rules, we've always got to define where we're starting, and then we write a rule for finding the next term. So in this case, we're taking the previous term times 2. Now we are repeatedly multiplying. So if you remember from our unit and exponential functions, that is raising 2 to a power. That's repeated multiplication. And again, like before here, this is term, if we write our n numbers here, this is 1, 2, 3, 4, 5. And if we write below that the number of times we've multiplied, we've not multiplied by any 2's here, we've multiplied by 1, 2, 3, 4. So the number of times we've multiplied is 1 less than n. So our explicit rule is going to be here the starting number, which is 1, and then times 2 and raised to the n minus 1. So this, remember, exponential raising a base to a power is equivalent to repeatedly multiplying by that number of 2's. Okay, over here, again, it's not, if we subtracted these, we don't get a common difference, but you might recognize these are all, as we're going, we are dividing by 3, and our sign changed to negative here, so we're dividing by negative 3. And remember, dividing by negative 3 is the same as multiplying by 1/3. So we're multiplying by negative 1/3. Here again, times negative 1/3. Here times negative 1/3. So you can see on these, when we're multiplying, when we have a number here that's our common multiplier is negative, notice that we alternate signs. So if we write our recursive rule, our first item is 81. And to get our next item, we take the previous item and we're multiplying it by negative 1/3. And just like we did over here, we could write the explicit formula for that using our exponential notation. And again, we're multiplying by 1 less than the term number. And again, we could use these over here for finding like the 15th, 20th, 30th term. Usually on these type of series, we won't be finding the 100th term because you can see, since this is like an exponential function, it is growing rather quickly. These functions where there is a repeated multiplication are referred to as geometric sequences. And they are another way of modeling an exponential function. And we could have pointed out on the last slide when we were talking about these arithmetic sequences, these equations that we have here, this is a linear function. Okay, so let's look at another type. Now this one, if we look at for a common addition here, I added 0, I added 1, I added 1, I added 2, I added 3. There's not clear there's a pattern there. And this is times 1, times 2. This would be times 3/2. This would be times 5/3. So this is neither, it's not arithmetic. and it's not geometric. But we can look at, can we find a pattern? If we look out here, if we look at the two previous numbers, notice here 2 is the sum of those two numbers. So let's see if that works here. So when I get to 3, that's the sum of those two numbers. The 5 is the sum of those two numbers. The 8 is the sum of those two numbers. So many of you have probably heard of this before. This pattern is called the Fibonacci sequence. Discovered or invented by an Italian mathematician. And if we write a recursive rule for this, on this one we have to actually identify the initial two numbers called the seeds. So a sub 1, the way I've written this, is 1, and a sub 2 is 1. And then once we get beyond 2, we take the previous two items and add them together. And again, this would be for n equals to 3 to infinity. The first two terms we have to determine explicitly. So this would be our explicit rule for this function, our recursive rule. I did some research. The explicit rule for this is a very complicated function notation and formula. It's not something that we're going to be able to come up with easily here. So if you're interested in that, you could do some more research. Fibonacci sequence, some of you have maybe seen. People see evidence of the Fibonacci sequence in nature. Some people, when they look at the spiral shell of certain snails in that spiral, when they measure the size that the spiral is expanding, they see patterns of these numbers. Sometimes if we can model the reproduction of rabbit populations using these models. So there's a lot of people that have interest in trying to find these patterns in nature. And also when we take ratios of numbers in the Fibonacci sequence, that's referred to as the golden ratio. And those golden ratios, when they're applied in art, tend to provide perspectives that are pleasing to the eye. So let's sum up. So again, this was neither of the two specific sequences that we started with, and there are lots of other special sequences that we could invent. You just try to look for patterns when you're looking at a sequence. Now we're going to wrap up here and focus on our sequences summary, and in particular these two types of sequences. So an arithmetic sequence is one where when you look at adjacent terms in the list, there's a common difference. And we can write both recursive and explicit rules for the arithmetic sequences. When we write a recursive rule, we have to prime the rule with the first number, whatever that is. That would be the first term, a sub 1. And then to get to the nth term in the thing, we take the previous term, which would be the n minus 1 term, and add d. And this was our formula for getting an explicit rule. Again, d is our common difference. Geometric sequences there's a typo here. This should be a common ratio here. Let me see if I can get rid of that. So common ratio. And the recursive rule, again, we have to prime it with the starting number, and then we take the previous number and multiply by our common ratio, and an exponential function for finding the explicit item. So let's wrap up looking at some sample problems like you might have for homework. So in these sequences, we are asked to determine whether they are arithmetic, geometric, or some other type. And if they're arithmetic or geometric, we want to write a rule for the sequence. So a good item when we're dealing with sequences is to check for our common difference, or to calculate the difference between adjacent terms. So here the difference is +2. Here the difference is +4. Here the difference is +6. So it's not arithmetic. And if we look at the ratio to look for a common multiplier, here I'm going to take 3 divided by 1, so this is times 3. This would be times 7/3. So we have different numbers. So there's neither a common difference or a common ratio, so this sequence is neither geometric or arithmetic. You can see the pattern here that we would be adding 8 and 10 and 12, so there is a pattern to this, and we could write a recursive rule for that, but I'm not going to take the time to do that. So let's check this next one. So let's see if there's a common difference. So going from here to here, we're subtracting 4. Here to here, we're subtracting 4. Here to here, we're subtracting 4. So our common difference, which is D, equals -4. So we'll write an explicit rule for this. So our explicit rule, using the formula that we had on the previous chart, is going to be a sub 1, which is 3, plus our common difference. So that'll be -4 times n-1. Now I'm leaving this in this form so we can easily see the pattern. We could distribute the -4 and simplify this and come up with a reduced or simplified formula for our sequence, but we're just going to leave it in this format. Now let's look at our last one here. So if we look again for differences, here we're +3, and here we would be +6. So it's not a common difference. Let's look at a ratio. 6 divided by 3 is 2. 12 divided by 6, so this would be times 2, again times 2, times 2. Many of you maybe saw that already, that we were multiplying by 2. So this one is geometric. I forgot up here with this one, we should have written out it's arithmetic, with D equals -4, and this was geometric with R equals 2. And our explicit formula here is going to be the first term times 2 to the n-1 power. So good luck with seeing patterns and writing your sequences.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?